Unconfined compressive strength is a means of conservatively determining how much bearing pressure a soil foundation can withstand. It is a conservative estimate because the soil or test column is not confined by surrounding soil that would normally be in place during field conditions. So imagine a soil column pulled from the ground without any confining pressure, as shown here. If we broke such a specimen that could remain intact, then the results would not emulate field conditions. The compressive strength would be much higher in reality because surrounding soil would confine such a specimen, increasing its ability to resist vertical forces. Geotechnical engineers can utilize this test to obtain a quick and conservative soil strength value if undisturbed samples are available from the site in question. The objective of the unconfined compression test is to find the ultimate compressive strength. In order to do so, we apply axial stresses to the sample without confining stress. Thus, the soil must be capable of standing alone, so fine-grained soils or rock are commonly used during these tests. The equation listed here is defined by sigma 1 and sigma 3. Sigma 1 is the axial stress, which is the same in the top and bottom directions. And sigma 3 is the confining stress, which is negligible here because the sample is not confined from its side walls. The specimen stands alone under axial pressure, therefore sigma 3 is 0. Then, unconfined compressive strength can be expressed simply as the axial load divided by the area normal to the axial load, P divided by A, normally expressed in units of pounds per square inch. We will record a load value during the test read off directly from the transducer, then later convert this load value, P, into a stress by dividing by the cross-sectional area. The same methodology is used in breaking concrete cylinders. Undrained shear strength is often reported along with compressive strength. Unconfined shear strength is defined as 1/2 of the unconfined compressive strength. Thus, undrained shear strength can be written this way. Strain is defined as the ratio of change in specimen length to original specimen length. We will record displacement, delta L, from the LVDT while simultaneously recording load values from the transducer, P. A stress and strain can then be tabulated from the raw data. After the test, a stress-strain curve that fits the data set will be constructed. When compressing an unconfined specimen, naturally the height decreases and cross-sectional area increases. As the sample is compressed, the area gets larger and larger, assuming no total volume change throughout the duration of the test. So with each reading, a strain can be calculated. With strain, this relation is used to estimate the actual area. This actual area will be the area used to calculate the stress on the sample, A0 over 1 minus the strain. It is best to use an undisturbed sample when running an unconfined compression test. Here, a Shelby tube sample is extruded with a hydraulic jack. The jack fully pushes the sample out. Carefully remove the sample from the bottom platen of the jack and place on a flat surface. Trim or cut the sample as necessary. If the sample is cut, ensure that the ends are flat. Also ensure the outer diameter of the sample is not out of round. Take several diameter measurements up and down the length of the specimen and average the readings. Take several length measurements around the perimeter of the specimen and average the readings. Record the average readings and weigh the specimen. Weigh a tare and put the extra unusable soil into the tare for a moisture content determination. Weigh the tare in wet soil and oven dry at 110 degrees Celsius overnight. The Shelby tube sample was 4.573 inches in length and 2.227 inches in diameter. Thus, the cross-sectional area came to 3.895 square inches. Finally, the total volume of the specimen is calculated to be 17.813 cubic inches. The total weight was 426.6 grams. The moisture content determination came to 81.2%. It is important that we do not load our soil too quickly, causing it to prematurely fail. So the ASTM specifies a range of acceptable loading rates for soil test columns. The range is specified as 0.5% axial strain per minute to 2% axial strain per minute. This makes the loading rate dependent upon sample length. By rearranging the strain equation and solving for delta L, i.e. height change per minute, we solve for the range of loading rates that are accepted by the standard. 0.5% strain per minute yields 0.022865 inches per minute, and 2% strain per minute yields 0.09146 inches per minute. We will use the lower bound rate to ensure the specimen reaches its maximum capacity before failure. Position a vertical LVDT so that it measures upward movement from the bottom platen. Cap or place a flat disc on top of the specimen and raise the platen so that it just makes contact with the load cell. We will be measuring displacements from the vertical LVDT with simultaneous loads from the transducer. Set the loading rate or motor speed to the desired setting. Tear or zero out the digital readouts from the vertical LVDT and load cell transducer. Press the up arrow to start the test. This raises the platen at the desired motor speed in the upward direction. Record displacements and loads from the digital readout at equally spaced intervals throughout the test. The standard requires at least 15 data points. We took readings every 10 seconds. Notice how the readout values displacement, named DISP1T, and load, named load2T, values rise. Also notice how cracking occurs at the base of the sample. Run the test until the load values begin to steadily decrease. This is a good indicator of failure. In our case, the test specimen was classified as a soft alluvial clay, and it continued cracking before actual failure was achieved. Failure did not occur until shear cracks propagated through the specimen. Then load values began to decrease. Notice the two shear propagations on top and bottom of the specimen. These are the natural failure planes. Cohesive soils and rock will display such failure planes when failed in compression. The chart shown here is the first step to the data reduction of the unconfined compression test. The first two columns display raw data from the digital readout throughout the test, load and displacement. The third column, strain, is displacement divided by the original sample length, and this quantity is unitless. The actual area is the next column and is calculated by dividing the original sample area by 1 minus the current strain value. This increases the cross-sectional area of the specimen as the length decreases. Pressure or stress in the last column is next calculated by dividing the load by the current actual area value. Now we can plot stress and strain against one another and extrapolate the maximum stress and failure strain values. Stress in units of pounds per square inch is plotted on the y-axis, while strain is plotted on the x-axis. Notice how there is a linear increase in stress within the early portion of the dataset. After the linear portion, the data begins to tail off and a maximum or peak is achieved. Failure occurs after the spike and stress values decrease with an increase in strain. This is typical behavior of cohesive soil failure. Finally, the peak stress value is extrapolated with an associated strain. The extrapolation is indicated here in red. The max stress of the specimen before failure came to 6.815 pounds per square inch at a strain of 14%. The unconfined soil column can handle 6.815 pounds per square inch of stress before critical failure. Again, this is a conservative means of estimating bearing capacity because the soil is not confined from its side walls. This concludes the test procedures and data reduction sections of the unconfined compression test.